For the filter circuit shown, we're asked what is the magnitude of the transfer function, V0 over Vs, so that's our h of s, it's equal to that, at a frequency of 10.9 megahertz. Then we have some more values here. So this is what we're going to do, and it can be used for any circuit like this, and we're going to see first if it's a low pass or high pass. This doesn't necessarily decide how we would go about solving the problem, especially if we start with the voltage divider method, which is what we've been using a lot recently. And so by this point, we should be very, very familiar with it. So voltage divider is where we have our output voltage, V0, equal to the input voltage, and it's being multiplied by the impedance that it is over. So this impedance that's tied to the output, we have our RL, and then we have our RL down here, and then we have plus whatever impedance is happening over here. And so this is just going to be RS plus our CS for this. But since we want it in the transfer function, we want the magnitude, we need to convert it to the time domain. So this CS is really going to be our Z of C, and it's equal to 1 over J times omega times our CS. And so when we rewrite this, since we have an imaginary number, we could flip our negative around. So it's actually going to look like the following. That line's still there, where we have a minus J with our omega times our CS. And so this is going to be our equation. Now the Vs is going to be divided by both sides, so we get our V0 over Vs, and that's how we get our V0 over Vs. Now we're given frequency, not our omega, but we know that omega is equal to 2 pi times our frequency. So when we write this out, we can substitute this in. We have our h of s, which means the transfer, is equal to our V0 over Vs, and this is equal to our RL divided by our RL plus. And there's also simpler ways to go about this. If you know the actual workings of this, you just plug the values in, but we're going over the actual concept of it here. And this is also a way to make sure you get it correct. So from here, we actually don't need the parentheses anymore because our RL and our RC are both the constant resistors. And we're going to have to do this imaginary number stuff later in a second. Or we're going to do it separately, not later. We're going to do it right now, but separately. So we have minus, we have our J, which is basically I for imaginary number. And then inside of here, we're going to have our 1 divided by, because when we factor out the J, we just have a 1 on top. We have our 2 pi times our frequency, which here is 10.9 megahertz, mega being 10 to the 6th, times our capacitance, which is 3.7 picofarads. And pico is just 10 to the negative 7th in, or I'm sorry, 10 to the negative 12th in measurements. And so what we're going to want to do is look at this first. So we're going to plug this into a calculator, and if we do so, we're going to get this. So our value here is going to be approximately 0.51503. That's going to be answer for this. Now, what we're going to do with these is we're just going to add them together. So we have our RL plus our RC, and for this problem, it's going to total out to be 20.1 kilo ohms. Now our RL, we know, is 13.6 kilo ohms. So this right here is 13.6 kilo ohms. We can see that we have kilo and kilo here. Now, if we wanted to, we could make this kilo also. So right now, this is just measured in ohms, or not ohms, but just the measurement here. And so what we're going to have, what we can do, is say, well, we want this in kilo. So we're going to multiply it by 1 kilo over 10 cubed, because a kilo is 10 cubed. And so now we want to find the magnitude. This is important. When we look at the magnitude, we know that our mag, and we're solving for voltage here, so I'm just going to say Vm, is equal to the square root of our real number squared plus our imaginary number squared. And if we wanted to find the angle, our angle is equal to tangent negative 1. Oh, so that's arctangent of our imaginary number over our real number. But we don't care about that now. We're not looking for that. We're looking for the magnitude, not the angle. And so what we can do for this is we're going to convert it. So this top one is just going to be 13.6 kilo ohms. Still, and that's because we don't have some other value right here. So if we plug that in here, it's just going to be 13.6, and you can see that if you plug it into a calculator. For this bottom one, we are going to have to change it. And we're plugging this value and this value, we're squaring both, and we're putting them inside of here. And we can see that this capacitance is actually so small that it barely affects our magnitude right here, this Vm. And remember, we have our magnitude and then we have the angle. And so what we're going to be left with is essentially 21 or 20.1 kilo ohms, just like this. So small. And you can see that if you plug it into a calculator. It's good to do that as well. And so from here, we could just cancel out the kilo ohms, the kilos, and then we could just divide 13.6 and then the 20.1. And if we do so, we're going to get 0.67662 as our answer. And that's how we would look about solving for something that looks like this and this exact problem.